Hello everyone, my name is Avkash and today we are going to cover NVIDIA NeRF implementation to build 3D models using videos or a collection of images using tiny CUDA neural network framework. In today's videos, our objective is to start from a video input to generate various data points through various camera points using colmap Python library. Once the input data set is ready, then we are going to use the NVIDIA NGP or neural graphics primitive library to train our model so that we could generate either NeRF, neural radiance field, or the SDF, signed distance functions, or the neural images, or the neural volumes. This tutorial is divided into three different segments. First, the environment or the machine preparation. Here I will be using Ubuntu 22.04 operating system. So I will be showing you to prepare the environment so that you could compile NVIDIA NGP library. That was the biggest time-consuming task. It took for over a day for me to prepare my machine. So I have a lot of information to share. So if you are using Ubuntu 22.04 for NVIDIA NGP compilation, this tutorial is going to be very handy to you. The second part, we are going to ingest a video content and generating the multi-hash point data input, which means we are extracting the various images from the video and a JSON file to explain all those data points related to the images extracted from the input video. And in the third step, we are going to train a neural network so that we could generate the neural graphics primitive, or in layman term is a 3D mesh point. Once training is completed, we are going to look various ways so that we could play with the data, we could generate the mesh, we could set up different camera angles, we could learn how to play with the result output and save the models which we have generated through NVIDIA NGP library. So there is a lot to learn in this tutorial, so let's get ourselves started. At first, I have CUDA version 11.6 and the NVIDIA driver is 510.73.05. The NVCC is 11.5, which is mismatch from CUDA. GCC and CMAX are okay. Looking at the requirement, I do have CMAX 323 updated and GCC is also latest. Now, if you have cloned the repo using these two commands, it means you are ready to build using this command, and it's using the CMake. First you run this command build. After that you can run the second given command, and running this command is going to give error if your environment is not correctly set to build the NVIDIA NGP module. This is a very common error. So after the error occurred, I decided to solve problem one by one in multiple steps. Very first, I decided to install the NVIDIA Optics, which is an optional component, but I decided to install it. And after the NVIDIA Optics driver download, the driver was installed at my local machine. Here, as you could see, the driver is completely installed, and after the driver is installed, I have moved this driver to user local in the optics folder, so user local and optics folder. And after that, when the CMake build command is going to be run, below you could see that it was able to find the optics, and it can also match with Titan XP driver. So these two matches were done. Now I try to install 515.48.07 using the Ubuntu software updater. However, I was not able to get 48.07. Instead, with this NVIDIA driver 515 proprietary built-in support, I was able to install the 515.43.64, which is still okay. After the driver was updated, I did update the Ubuntu kernel also, and when I installed the NVIDIA Cuda toolkit using the built-in method, I found that even when my Cuda version is 11.7, however, the NVCC version, which was installed by the default NVIDIA repo, was 11.5, so that was a mismatch and it caused my problem to build the NVIDIA NGP module. So the best way to install the Cuda toolkit was to use the NVIDIA download Cuda toolkit 11.7 directly from here, because when you install this 11.7 from here, that is actually what is going to update your NVCC. So finally, using these commands, I was able to install the Cuda toolkit in my machine, and as you could see here that 518 I do have the kernel updated. I don't have command to show, but I was able to update. And then after, as you could see here, that my NVCC version is updated to 11.7, which matches, and my Cuda 11.7 is also installed here, which I have set into my bash script. So it's also set into the path, and it uses the 11.7. And the NVIDIA driver also shows that the 515.43.64 and the Cuda version 11.7. So almost all of my environment is really ready for me to build the NVIDIA NGP library without any problem. So if we try to match my final environment, that is exactly I have Ubuntu 22.04 with kernel 5.18, Cuda 11.7 with driver 515.43.04, which matches with my NVCC 11.7, and the CMake, G++ and GCC all updated version. The next step for you to make sure you have all of these packages installed in your Ubuntu or the Linux distribution. At this point, your environment must be ready to build the NGP package. I already have complete recursive instant NGP cloned. First build command went complete without any problem. Next, I will be building and if your environment is ready and you do not have any problem, this build command will be completed successfully. And here you could see that my build is successful. There is test bed is also created and the PyTorch, and we can test that into the build folder. So here is the test bed and here is the PyTorch library. Now we are going to build our own dataset through a video. So here is the video which I have. This video is about 100-second video, and the video is created by keeping the object centered and taking full video from all different sides from a little above angle to the object.
So this input video is available at ngp work JCB folder. So this is our source video and that is our source directory. If you would want to create your own dataset, here is the link, and here you are going to find the details about creating your own video and the command. And the command is that we are going to use the colmap to NeRF.py that is also available into the scripts folder, and that's the colmap to NeRF. So this is the file which we are going to use, and we are going to pass our input video here. Next command is the frame per second, how many frames we want to extract from the given video. So it's like a 2 frame per second. If we choose 2 frame per second for our 100-second video, we are going to get 200 frames. And run colmap, because we need to run the colmap so that we could get the camera locations, and we are going to use this AABB scale, and the value is 16 here. There are a couple of things to remember is that when you are going to use the 16 value with AABB, it is possible that you may not run your NGP library correctly due to several different types of graphics card capabilities. So the solution is to, if you are using the Titan XP CUDA, it's better to use the AABB scale 1 to 4, and if you are using the higher version of the RTX newer versions, then you can use the AABB scale even up to bigger. So for my example, I will be using the AABB scale 4 because that works for me. So here is our command. So I will be using the command here, Python, and just to make sure that I do have the Conda 3.9. So my Python version is 3.9 from Conda. So I will be using Python, then scripts, colmap to NeRF. So that is the command. The video in, here we are going to use the file from our source work, GP work, JCB, and JCB.mp4. However, if we try to look into this colmap to NeRF, I can show you that here you could pass the video in, different frame rate, several other parameters are available, and here is the dot dash dash out. So where the transform.json you would want to save it. And if you are not passing the video, you are passing the images, then you could pass the images from here, and here is the AABB scale. So there are some other parameters available that can be reused as if needed. And if you would want to save your output in different directory, that's where you could use this dash dash out. So here is our video in. Next, we have to use video frame per second, and here I will be using the 2 frame per second. Then run colmap and ABB scale, and here ABB scale is, I'm just using 4, and dash dash out, and my target is to create the transform.json in the same folder where the JCB file is, and then you could save the transform.json. So that is the full command we have created. I will keep this command here, just a typo here, it's dash dash run colmap. Yes, it means it will create the images folder extracted from the video, and it will be in the same location where the JCB MP4 or the source directory source video is. It's reading the video, and then it's finding that how many videos, how many images will be extracted. say yes, and at this point the number of images will be calculated. And because our video is full HD 1920 to 1080, the system decided that there will be 201 images for the 100-second video. Now the 200 images are being generated, and then finally the transform.json will be created. So I will go ahead and fast forward this whole process. Finally, our build is completed and the transform.json is created in this JCB folder. We could take a look at that. So that's our transform.json. Here you could see that all the images are used, some of these configurations, and all those images we could also see are in work, NGP work, and the JCB folder. Here is our very latest transform.json and all the 200 images or 201 which were being extracted from the video are all available here. So this is the transform.json, and for every image there are various parameters available. This is the transform matrix, sharpness, and for every image, and these are the settings which are the global settings, and some of these settings can also be updated based on this document. And here you could see that there is a scale and there is an offset. So these two settings are currently not added here. ABBV scale, which we have already used 4 to start with. So now we are good to go and we could start using our input data. So to use the input data, we just really need to pass the transform.json, and we just need to use this testbed library which we have just built. So let me come back here. First I will run the NVIDIA SMI. So you could see that this is our current state of NVIDIA Cuda library. The next step is to use this build testbed. So we already build testbed. So that's the library we have. Now we need to pass the scene, and our input is going to be the work, NGP work, JCB, and transform.json. So when this transforms.json will be loaded, it is going to use this file path for every respective image. So there is one trick I am using, because as you see here that these images are not respective to the library. So the best way to solve this problem is that remove these images and make sure that they are actually loaded from the same place where the transform.json is located. So I will replace this whole path with this whole path will be replaced with the images. So in this scenario, now this is the transform and the location is image. So all the images are loaded from directly from the same path. So that's how you can solve this problem. Now if we run, at this point all the images are read correctly and your training is started. So here the training is started. Here are the default batch size for the number of data points. At this point, if you will be looking into the, and you could see that this testbed application is using the Cuda, and it's about 6 gig RAM it is using. Here now I'm using zoom out option so that I could focus on the image. And here as you could see that our object is being visible while the training is still going on. From this direction, you could see that that's the object, and I'm using mouse to rotate, and as the training will grow, the clarity related with our object will be more clear, and that's the mouse control. At this point, while the training is still going on, I will be showing you a couple of controls. So here is the NeRF rendering options, and here is the crop AABB. So here you could see that our object is, once we open this crop section, we are going to get these box where this is the whole world is available for us. And now using this cropping, we could adjust all X, Y, Z. So I will be showing you the master. So this is the master crop. So if you see here, when I'm moving, my box is slimming, and that's how I am reducing the environment so I can focus a lot more to my core object. And I will try to twist it to make sure that all the content related to my object is still good. Now if you see here that depending on our content, we have to clear the bottom part. So I will be using the Z and see what happens. As you see, this is Z here. This is another Z. And let me use this Z. So let's see Y. You see now this Y is helping us to remove the noise from the bottom. And let's try to zoom in. And here is our object. We do have some noise at its left, so we could clean that part as well. Let's see back part. We can also reduce from here. Now we have cleaned it up quite a lot. We can also clean some of this area, but the clarity is quite good at this point. Let's see the Y little more. That is going to cut the bottom, and we were able to clean up the environment quite a lot. And at this point, crop AABB, I will close this. So now the box is also gone. If we would want to reduce this width, and now here is your object. At the next step, we are going to look the debug part. And here you see there is a debug visualization. Here we can look into the cameras, that how the cameras were recorded, and that is mostly data is coming out from colmap. So if I try to reduce this, this is how you could see that the different cameras, and mostly I was creating this video from the top angle, and so these are the cameras which being extracted, and that's like a per image. So we have 201 images. So these data points, you could see that how the camera was used. If I would have used the camera at the object level angle, that would have also been visible. You can zoom in or you can zoom out. So that's come out from visual camera, and now you can see that visualize unit cube, and that's what really shows that where this object is. And if you would want to adjust this object properly, you can actually use the scale part which I was talking earlier, and that's where this is. that you could use this scale and offset, that how deep you would want to fit this image properly within the given cube. At this point, if you are satisfied with the object, you could remove this camera and remove this cube. If you would want to set these visualization, you can also use this parameter, which I am not really using right now. And here comes the mesh. If you would want to create a mesh from it, here you could see that we were able to successfully create a mesh from it. If we could clean this area of noise, then our mesh would have been created even much more better. If you would want to save mesh density, that's these two are save option. Here you could clear the mesh. At this point, if you would want to save the snapshot, you can come here, and here is your snapshot. So you could save it and transform, and if you can actually give a name, transform base, and here is the, I would call it 0 1, and that is going to save this mesh. So it's transform 0 1, and we can validate that. And here is our base 01 MSG path 328 meg file is saved. It means that we have saved our snapshot. So if we would want to reload, we could actually give the file name and we could reload from here. There are several other parameters which you could use. Here is the histogram. Here you can see the details about histogram. The resolution, if you would want to change the render mode, color space, you could change. There are various render modes are available. I found the shade is the most appropriate. It works. If I change to depth, you can see the results. Slice, positions. However, the most appropriate is the shade, and that's what we are keep seeing it. If we want to change the resolution of the mesh, so most of the STF or the other examples which are available in this NGP library, you could run, because once your compilation is done, most of these examples can be run without any problem. So I have already downloaded this WDS Cloud Quarter, which is validated. Mode will be volume, and our scene will be the WADB as suggested here. Let's run it. And that's how you could take a look at the volume, and here is the light. You can also use the testbed library to reproduce the Gigapixel results. And for this example, you can download the Gigapixel image directly from here, and that will be your 1.2 Gigapixel Tokyo Shibuya panorama image. I have already downloaded that image, and that's the about 180 meg for the 1.2 gigapixel, and if you would take this extra large image, that will be about 5 meg of this file. So once you have downloaded those images, you could run this convert image, which is also part of the scripts convert image, and that's where the convert image code is. So you could pass a JPEG image and that will convert that image to a binary file. So that's the image conversion, and you can pass your image and output will be your binary. So I have already converted these two files, both 1.2 gig and the extra large here. Because my GPU is the older version of GPU, so I will not be able to load this 1.2 gigapixel image, but I can give you the example of loading the extra large image just by using this command. So we are using the build testbed scene, and we are using work Gigapixel and Tokyo 10, and then I'm using this binary file, and that's where the image is loaded. And again, this is just a flat image, so you will not be able to see these controls related with our data mesh. At last, I will suggest you to please follow up the documentation. If you would want to build your own data set, you could use this documentation. That is going to be very helpful for you. Make sure you have all the required libraries installed in your machine, and while using this product, if you have any problem, please reach out to me either through my GitHub related with this tutorial or to this YouTube video comments, and I will be very happy to assist you.